Okay, ladies and gentlemen, I'm back for video number 5 on motion. And we started talking about Newton's first law, we got into Newton's second law, and we have yet to do Newton's third law. I'd quickly like to review the first and second laws because I have here a spinning bicycle wheel. And the laws apply to something rotating just as well as something moving a straight line. So let me, and by the way, the reason I'm doing this is this bicycle wheel has very, very little friction compared to the cars and the inclined plane that I have. If I give this a little push, notice it just keeps spinning because the real friction is a little bit of air friction plus a little bit in the bearings, and I've oiled the bearings, so it tends to go on, and you can see more clearly what is meant by Newton's first law. This wheel is a little bit out of balance. Let's get it to stop. If it was balanced, it would stop anywhere. Now, Newton's first law says that this wheel will stay stationary forever unless there's some outside force that causes it to accelerate. Now, this is going to be a rotational acceleration, but it doesn't make any difference whether it's linear or rotation. This bicycle wheel, according to Newton's first law, will stay here forever unless something exerts a force on it, okay? In fact, it would be a torque, but we'll just say a force at this time. Now, Newton's first law says it'll stay there forever unless something exerts a force and gets it moving, and if it's moving and there were no friction, it would continue moving forever. So now I'll apply that force. Here's the force. I've applied a force to it and I see that it's moving. And in the case of the wheel, it's very easy to see that it's moving at the same speed. There is a little bit of friction. After about an hour, it'll finally come to a stop. But Newton's first law says this will continue spinning forever if nothing stops it, like my hand is stopping it. The second law we noticed, or we learned that how something accelerates, how it goes faster and faster depends on the size of the force. If I exert a little force, then this just accelerates slowly. If I exert a large force, the acceleration is large. Newton's second law says that the acceleration of an object is directly proportional to the size of the force and inversely proportional to the mass. Well, I didn't change the mass here. The mass stayed the same, but you can see if I apply a little force, I have a little acceleration. If I apply a large force, I have a large acceleration for the same mass. Well, that's Newton's second law, and that's a good example of that. The third law is also important, but it's not so obvious. And the third law says something very simple. It says that for every force in the universe, there is an equal and opposite force. For every force in the universe. So, if gravity is pulling down on me, then I'm pulling up on the earth. If this mass is pushing down on the table is pushing up on the mass. If this finger pushes on this finger, then they both experience exactly the same force. For every force in the universe, there is an equal and opposite force. And that's very important because if I ask you the question, what is the force that allows me to walk across this room? Well, the force is the force that the floor exerts on me. As I step forward, I'm pushing back on the earth, and the earth is pushing forward on me. Every step I push back, the earth pushes forward. If I was on ice or on a skateboard, I would push back, but the wheels would turn and I would have no motion. So for every force in the universe, there is an equal and opposite force. And those are the three laws, and I'd like to do a couple of more examples, and that will be the end of this program. I'll go back to Newton's second law, and we'll talk about how it's related to work and energy and those things. I love to make toys. I love to make things that are useful and fun, and almost all of them demonstrate physics in one way or the other. Bamboo is one of the most fabulous woods in the entire world. You can do so much with it. It's so strong, it's so stringy, and it's so flexible that I can make children's bow and arrows. I also make out of different wood beautiful bows that can be used for target shooting. This is mine. I made it myself in this workshop. I also made these small ones out of bamboo because bamboo is so easy to work with. And what I want to get at is the following. We're going to deal kind of with all of Newton's laws in this example. If I take and put up a target here, then I can talk about what I'm doing. This bamboo is elastic. When I pull back on the arrow, I am creating potential energy in the bamboo bow. The force that I exerted did work. Just when I lift the mass, the force that I exert upward does work, and this mass has potential energy right now. Well, likewise, this arrow has potential energy. I did work to put it here. If I release it, the system, the bow, will do work and will accelerate the arrow as it does work on it. It will give it kinetic energy. So you can see I can fire the arrow into the box over here, and the whole physics that occurred is quite interesting. Now I'm doing work. Well, let me put my arrow back in here. Now I'm doing work. The work occurs as potential energy. When I released it, the tension in the bow exerted a force on the arrow that accelerated. Another way of saying that is the potential energy that we had stored in the bow was converted into kinetic energy. If I had a large fat arrow here, the arrow wouldn't accelerate as rapidly, but it would end up with the same amount of energy. That's important to understand. So here we are. The work that I do goes into potential energy. The potential energy is converted to kinetic energy as a result of the work done by the bow when it accelerates it. That's a beautiful example of the relationship between force